Welcome back. Episode 2, The Pure Math. Today we look at where Ladhe's numbers come from. The core idea is old. It goes back to Goldbach in 1742. What is new is how we use it, as a compact witness representation, for a hash commitment.
First, Goldbach in 60 seconds. In 1742, Christian Goldbach conjectured that every even integer greater than 2 is the sum of two primes. For example, 10 equals 3 plus 7, or 5 plus 5. 100 has many such pairs. The conjecture is still unproved, but verified for all numbers up to about 4 times 10 to the 18th.
We do not actually need Goldbach itself. We need a small variation. Pick a prime p. Find a tuple of distinct odd primes, in increasing order, whose sum is exactly p. We call such a tuple a decomposition of p. There are many decompositions for any reasonable p. That diversity is what we are going to exploit.
Why specifically an odd number of primes? Pure parity. Odd primes are odd numbers. The sum of an odd count of odd numbers is odd. The sum of an even count of odd numbers is even. Our p is itself an odd prime. So we need an odd count k of odd primes summing to p. In Ladhe we use k equal to 3, 5, or 7. Different k values give different witness sizes.
Let us look at a small worked example. Take p equal to 167. Here are some valid decompositions into distinct odd primes. 3 plus 7 plus 157, 3 plus 61 plus 103, 3 plus 5 plus 11 plus 47 plus 101, and longer tuples are possible too. Many tuples sum to 167. Any one of them can serve as a witness.
How many such decompositions exist? For real cryptographic primes, the number is enormous. For a 1024-bit p, the number of valid 3' decompositions is roughly on the order of 2 to the 1014th. That is comparable to the security level of pre-quantum RSA, not because finding a decomposition is hard, but because there are so many valid ones for the signer to choose from.
Now the engineering trick that makes Ladhe compact. Take the decomposition P1 through Pk. Instead of storing all k primes, we store the indexed pair compression. We pair them up from the start, and since k is odd, the last element stays unpaired. For our example with 5 primes 3, 5, 11, 47, 101, the compressed witness becomes 8, 58, 101, 3 numbers instead of 5. The verifier can do its job from this compact form, as we will see in episode 3.
At cryptographic sizes, this halves the witness footprint. Without compression we would store k full primes. With pair compression we store k plus 1 over 2 numbers. For a 1024-bit p with 3 primes, the raw form is roughly 384 bytes. The compressed form is about 100 bytes. That is the entire reason Ladhe signatures are so small. Compare with SPHINCS+, whose signatures are around 17 kilobytes. Ladhe signatures fit in roughly 100 bytes.
So we have a tuple of primes summing to p, and a compact 2 or 3 number witness W. Where does the cryptography come in? The signer keeps the prime secret. The signer publishes p and the SHA-256 hash of the encoded witness. That is the public key. Security comes from the hash. The only way to forge a valid witness is to find a preimage of the SHA-256 hash, and that is the SHA-256 preimage problem. No new hardness assumption. The same foundation as SPHINCS+.
To recap, primes summing to p give us the witness. Indexed pair compression makes it compact. SHA-256 of the encoded witness becomes the public key. Up next, episode 3. From math to signatures. We will watch Alice sign a document, and Bob verify it. Thank you for watching.